Hello everyone, thanks for coming. Today we are going to do a review of our week 9 lecture. So first of all, we continue our discussion on the Gram-Smith process. The Gram-Smith process converts a set of bases into a set of orthonormal bases. Consequently, if we put those vectors as columns in a matrix, then we get the QR factorization of that matrix, where Q is a matrix whose columns are the orthonormal bases, and R are the coefficients. R is an upper triangular matrix. Its entries are Ij equals to the inner product of Qi and Aj. So in this way, the least square problem can be greatly simplified to Rx equals to Q transpose T. So in this way, we avoid solving A transpose Ax equals to A transpose B, and Rx equals to Q transpose B can be solved directly using back substitution. If we treat the function space as an abstract linear space, and then we define the inner product as the integration of the product of two functions, then we can also define the norm, and we can also apply the Gram-Smith process to obtain a set of orthonormal bases. For example, the Fourier series, the basis functions in the Fourier series will form a set of orthonormal bases, and each function in the function space can be expanded by using the Fourier expansion. So the key ideas are that the functions could behave like vectors in the linear space. Orthogonality simplifies computation, such as the Fourier expansion. In the next chapter, we introduce the determinants. So first of all, we formally define the determinants for 2x2 matrices. The determinant of the 2x2 matrix is AD minus BC. So if the determinant is 0, then A is singular, otherwise it's non-singular. Geometrically, the determinant of the matrix is the n-dimensional volume spanned by the rows of the matrix. Also, if we reduce A to its echelon form, then its determinant is plus or minus a product of pivots. Also, the determinant of A would affect A inverse B. Basically, whether determinant is 0 or non-zero would help us determine if the columns are linearly dependent or not. If we swap rows of a matrix, that would result in a sign change in the determinant. If we multiply a row by a constant t, then the determinant is also multiplied by this t. If we add multiple of one row to another, then the determinant is unchanged. If one row is 0 in a matrix, then the determinant is 0. For triangular matrices, the determinant is a product of diagonal entries. Again, if A is singular, then its determinant is 0, and vice versa. The determinant of the product of two matrices equals to the determinant, the product of the determinants of those two matrices. Then we can deduce that the determinant of the inverse of a matrix is 1 divided by the determinant of that matrix. If we transpose one matrix, then the determinant of A transpose equals to the determinant of A. So the determinant, the quantity determinant, behaves well under elimination, multiplication, and transposition. Also, if we can obtain the echelon form of A, then its determinant is just a product, the plus or minus the product of the pivot variables. So formally speaking, how can we determine the determinant for an n by n matrix? So this is a big formula. All perturbations P multiplied by A1 alpha, A2 beta to AN mu where alpha, beta to mu is a perturbation of 1 to n. So each term selects one entry from each row and each column. Determinant P equals to +1 or -1 depending on the parity of row exchanges. We can see that the determinant is linear in each row and column. Swapping two rows or columns will change the sign of the determinant. Specifically, the determinant of the identity matrix is 1. We can also define determinant using the cofactor expansion. The cofactor of entry ij is -1 to the power I plus j, the determinant of mij, where mij is a submatrix formed by deleting row I and column j. So in this way, we can obtain the determinant using the expansion along row I. Determinant A equals to ai1 ci1 plus ai2 cofactor i2 to ain cin. We can also expand along column j using the similar formula. The cofactor expansion reduces n by n determinants to n minus 1 times n minus 1 minus. So it provides an inductive definition of the determinant of A, and it's also consistent with your primitive big permutation formula. Thanks for listening.